the last time we were talking about all this stuff, I had mentioned that I had added in like 3 additional slides to the original slides I put in there, because as I started thinking about transitioning over to multiple regression, I realized that I should talk about assumptions, because I had some slides about the assumptions that multiple regression sort of add, and I realized, well, I hadn't even talked about the assumptions for simple regression. So that's why I sort of added these in and talk about a little bit. They may sound familiar, they may sound completely foreign, but let's talk about what they mean and why we assume them. Every test that we do, they have assumptions. When we talked about t-tests and ANOVAs, we talked about things like homogeneity variance, and most of these things, they're these parametric tests. Well, they're called parametric tests because we assume certain parameters, certain things about them, mostly things like a normal distribution, and that the responses are continuous, things like that. So these are the same. These are the same types of assumptions we're talking about here. So the assumptions of simple linear regression, because it's linear regression, we're assuming that x linearly relates to y. There's a linear relationship. That makes sense. Even though we can actually get around that, and I'll talk about that in multiple regression section, that there are some ways you can sort of get around some curvilinear things using linear regression. But we are assuming that y is normally distributed. And taken together with the next thing, which is that data represent a qualitatively homogeneous population. I'll talk about that more in a sec too. And then we have this fancy like 50-cent word over here that's like throw around at parties and impress people. Homoscedasticity. Homoscedasticity. So X doesn't have to be, because as we'll see, we can use dichotomous predictors and ordinal predictors. We just have to do special things to sort of use them. But X, there's really no. I think if both X and Y are normally distributed to continuous variables, then we have your sort of traditional, regression that we're used to with 2 continuous variables. But X doesn't have to be normally distributed. The assumption is on the outcome, not the predictor so much. So this new word, homoscedasticity, is just a fancy word for when we have grouped predictors, we call it homogeneity variance because we can compare the groups. Homoscedasticity is really the same thing. It's just we're assuming a roughly equal distribution of variance across the predictor, so that basically the variability on the outcome is roughly the same at all levels of the predictor. That's a lot easier to test when you have just groups, because you just have discrete points to compare them, but it's the same assumption even when it's continuous. All right, so those are the things we sort of assume. And the ones you may not have heard of are things like homoscedasticity, even though you have. It's just you not heard that term before, that it said that way. But this idea that data represent a qualitatively homogeneous population, the idea is that we're trying to generate a model that explains what's going on. To do that, we're assuming that there's just one thing going on, that this particular model applies to everyone that's in the model. That's where down here, we assume things like no outliers. Well, the reason, and it's an assumption, but really it's not really an assumption. We expect it because we're assuming that Y is normally distributed. So there shouldn't be any outliers, because if you have a normal distribution, it shouldn't have outliers, it shouldn't be skewed, all that kind of stuff. But also, because we're expecting a qualitatively homogeneous population, we also expect no outliers, because we're expecting everyone to sort of fit in, that anyone that doesn't sort of work with that model, therefore doesn't really belong there. And that can happen in 2 ways. It could be distribution based, that somehow someone doesn't, is, an outlier in terms of the distribution, but it could also be that they are affecting the model in some way that is unusual or abnormally large relative to other participants. That could also make them an outlier. That's why it says both model-based and relative to the distribution of Y. So both of those are considered. I'll talk about that more in a second. We also, because of all this stuff, the homogeneity variance, we assume that there is a single consistent error term, that error is the same all the way across. That when we talk about a standard error of measurement, that we can use the same standard error of measurement to predict or to explain the distribution no matter where you are. It doesn't matter if you're high or low, it's the same error. Okay. So with most of these normally distributed assumption type models, we're assuming there are no outliers, right? Because of normal distribution and qualitative homogeneous population. And again, distributional and qualitative outliers, we're used to looking at distributional ones. A score sort of sticks out a little too far in a distribution, and we think, oh, or we calculate their scores, and oh, look, it's got a higher than 3.3, z-score or something, so it's likely it's very different than the rest of the population, the rest of the distribution. We don't typically think about the ones that are more model-based outliers. So there are some terms. These are some new terms that are nice to know when talking about regression. They apply a little more to multiple regression, but they still do sort of matter. So leverage is the distance of a score from the distribution. So the farther a score is out of the distribution, there's more potential for it to influence the distribution more. And then there's discrepancy. It's sort of the point doesn't really go along very well with the rest of the points. Like all the points are sort of on a nice line. You got a point that's sort of out there. That's discrepancy. Now, if you have leverage without discrepancy, that's going to have very little influence. If you have discrepancy with very little leverage, have very little influence. So you need the two of these, leverage and discrepancy, to change the regression equation with and without that score. So what do I mean? Let's do a quick example here. So if I have, my typical XY plane, right? And I have a bunch of points, all sort of lining up real nice. Okay. So this is probably a pretty strong relationship. We're going to have a nice, significant slope, all kinds of stuff. Now, what leverage is talking about is how far away. So if you think about there being a center, I don't know, somewhere in here, there is a center point to this distribution. Right, so the farther points are away from that center, the more sort of leverage they have. Like points out here have more leverage than points sort of towards the middle, right? So think of it like leverage in physics or something where, the longer thing, the farther something is away from the point in which you're sort of trying to pry or whatever, push, you actually have more leverage and actually helps to sort of move things more. So that's where that leverage comes from. Distance. But you can see the points that are distant, that have a lot of leverage, are also lined up very nicely, so they're not very discrepant. So because there's low discrepancy, they don't really have a whole lot of impact. Let's say we have a point that's like here, one point that's there. This point has both high discrepancy, all the points are going this way. This one point is sort of way off. And it also has a lot of leverage. It's far away from the point. What can actually happen to try to minimize this one residual that you may end up getting, instead of having a line that goes this way, it may actually flip the line up some other distance, and the line may go the opposite direction simply to try to account for that one point. So because it has high leverage and high discrepancy, it's very influent. It has a lot of influence. It's going to change the slope, change the correlation quite a lot. Or say a point out here, it has a lot of leverage and leverage, but because it has little discrepancy, it's not going to change the point, not going to change the line very much. All right, so when you have both leverage and discrepancy, you can get these model-based outliers where they have the combination of their predictor and their outcome score that's making them just a crazy outlier on here that doesn't quite go with everything else. So you might decide to sort of get rid of that particular score or something, because it's having just a crazy amount of influence on the rest of the equation. Right? You can actually flip it completely negative from where it is from all the other points. All right, so let's talk about all these sort of distributional things, just to show this is, if we actually did a regression and just plotted out the residuals, what you want to expect, the way we normally want to see it, is that all the residuals, the distances away, so this line now represents, it's a zeroed out sort of regression line, but it means that's where, you have no residual. And the distances between the points are how far away each predicted point is away from the actual score. You want to see this sort of box shape where the distribution is sort of about the same no matter where you are on this line. You're getting about the same variation in the residuals. Here, this represents some issues with normality, because it's skewed, where you're getting more points, larger residuals below, less residuals above. There's some skewness or something going on here. This one, you're looking at some non-linearity. So the residuals are showing you there actually is there's a curvilinear function in here that we're not capturing, and that's why the residuals are following that upside down U shape, or the other way, a U shape. This one's the one that's interesting. This is one looks at, it's called heteroscedasticity, where at very low levels of X, you're getting very little variation. The variance is very small. But as the sizes of X get larger, the variability in Y get much bigger. Right? So this is a violation of homoscedasticity called heteroscedasticity. All right. I'm trying to think of an example. There was an example I remember using some years ago, where somebody took people out into a field, and he told them, all right, as birds come over, flocks of birds come over, I want you to try to guess how many birds there are. And then somebody would take a picture of the flock, and they could then count exactly how many birds are in the flock. And what they did is they started to look at how good people's predictions were. Well, as it turns out, when the flocks are small, right, when you have small flocks of birds, people can count them pretty easily, and therefore the variability is not very big. But as the flocks of birds got bigger, right, their guesses actually became much more varied. Some people way overestimated, some people way underestimated, so they get much more variability as the actual flocks got larger. That makes sense. So this is an example of where you might see heteroscedasticity. You get this sort of funneling effect. So this tells you there's some issues with normality. This is issues with linearity. This is what you sort of want to see, the sort of random patterns. It's a box where everything you can sort of draw a line above and below, and it would say fairly consistent across all the predicted values. Okay, so what about non-continuous variables? We typically talk about, when we think about correlations and things, we typically think about Pearson correlations. That's the one that always gets sort of taught. That's the one that we, calculate covariance, divide by the product of the two standard deviations, and that's sort of a Pearson correlation. But there are other kinds. I'm not going to go too much into detail about these, but there are other types, which is like there's a Spearman correlation when you have two ordinal variables. It's called the Spearman rank order correlation or something like that. If you have two dichotomous variables, there's a correlation called the phi coefficients that actually tells you how related they are. It's very similar to doing a chi-square test of independence kind of thing, where it tells you if they're related. And you can even have one dichotomous and one continuous, which is called a point biserial correlation. So there are other types of correlations where you can have non-continuous variables involved. What about regression? So with regression, as long as the Y outcome is continuous, as long as it is continuous and fairly normally distributed, we can still do a simple regression using a dichotomous predictor or something. So for dichotomous predictor, you can use a simple linear regression. For ordinal predictors or predictors with more than two categories, we'll need to move to multiple regression because we actually have to break them up. So we'll talk about that in the next section. But if the outcome is not continuous, right? So if the outcome is continuous, this is still fine, it still works. But if the outcome is not continuous, then you need to switch to a different kind of regression. Like, for example, there's logistic regression that's designed for dichotomous outcomes or ordered polytomous outcomes, or sort of non-ordered categories like nominal variables too. There's all kinds of regressions. So there's no point in forcing a linear regression for an outcome that's not linear, right? Because the logistic regression takes into account the non-linearity of it. All right. So let's think about this. Let's say this is a simple example, and I have some people who are depressed are put into, they're randomly assigned to either a treatment or control condition, and we want to compare them. What kind of code can I use to compare these two groups? There's actually, for two groups, there's not a ton, but there is at least a couple different ways we could do this to compare them, and they actually have the outcome would be roughly the same, but it does illustrate the difference in approach. So how can we do this? How could we actually numerically code this that we actually could predict? Okay, so we can, it doesn't really matter the order, but just I usually think about, I don't know why, but I code this as 0, right? And a 0, 0, 0, and 0, okay? And then these will get a 1, 1, 1, 1, 1. Okay? This, using zeros and ones? Zeros and ones. We know what that's called. What kind of coding that is. I just think it's funny. Dummy coding. I don't know why, but that's what it's called. You use zeros and ones. It's called dummy coding. There's actually a particular way that the zeros and ones are used to be specifically dummy coding, but for the sake of argument, it's essentially dummy coding. How else could I do this? So here, having this predict this outcome, I would expect, what would I expect of my slope? I don't mean the number, but what things could I expect of my slope if I do it this way? If I code control 0 and treatment 1, given the depression outcomes, what would I expect of the slope? Yeah, it's going to be negative, exactly. Why? Because the lower number, 0, corresponds to higher outcomes in depression. The higher number of the predictor corresponds to lower numbers. So that's kind of nice, because if I want to show the treatment is lowering depression, getting a negative slope actually corresponds, right? It corresponds to that. What other code could I use with this? By the way, this approach of using dummy code, this is sort of akin to doing a t-test. It's going to compare this group to this group exactly, because when we actually figure out the y predicted equals whatever the slope is times x plus a, whatever a is. Remember, how do we interpret a? I mean, we spend a lot of time interpreting b, but how do we interpret a? Right, and so normally we think about, that's one of the issues that I have with how we typically teach regression, is that we're so concerned with this line and that this is the sort of y-intercept. Forget about that. Forget about that interpretation for a second. Yes, that is true. So what? In terms of psychology and everything, we don't care. We're across it so much. What useful information does this tell me? Besides that it crosses the y-axis. By the way, that was an excellent answer. It's just not the one I'm looking for. Right. When this is 0 is exactly it. When this is 0, y predicted equals a. So this is the value of a when y predicted is 0. So when in this predictor, when is x 0? Or x is 0 when you're in the control group. So what you're going to get back here is that a ends up being the mean of the control group, because that's what we coded it as. The slope will then tell you how much the treatment group differs than the control group. Right, so this becomes the control. This becomes the control group, and then the slope becomes the sort of difference between the control and the treatment group. So that makes it like a t-test. It's a direct comparison between them. With me so far? What other coding could I use that would make some sense? By the way, you can use any coding, but for the coding to make some sense, what other types of coding could I use besides zeros and ones? So this is dummy coding. Has anybody heard something like contrast coding? That ring a bell? So what if instead I use ones and negative ones. Differentiate them by ones and negative ones. Now what happens? We have our y predicted equals bx plus a. What's a now? How do we interpret a when we have ones and negative ones? Ones and negative ones. It's oftentimes called orthogonal or whatever, but it's basically just a form of contrast encoding. When is x going to be 0? Yes, that's exactly right. This now becomes the sort of grand mean of y. Do you understand why that is? So I'm going to have a mean for this group altogether, because they're equal. I have 5 and 5. If I average this group and this group together, take the two averages and average them, I'm going to get this sort of average. I'm going to get the average of all the y-stars, be the grand mean. And what the slope's going to tell me is this slope now, instead of telling me how far the groups are apart, this is how far the group is from the grand mean. What's that sound like? Where do we take group means and compare them to a grand mean? So yeah, it is part of a sampling distribution, and it is we are sort of doing that, but we're particular in this particular case. Instead of comparing one group directly to another, we're taking the two group means and comparing them to a middle grand mean. There's a statistical procedure that we do for that. So, that again? Yeah. So it's turning the between groups difference into a variance, and we use that in our F test. So when we use zeros and ones, we're going to get back, basically we're setting this up for a t-test. But if I use ones and negative ones, I'm now setting up there to be some grand mean, some mean that's right in the center here, right? That is going to, there's a mean directly in the middle here that's going, that is now separated into two groups, and we're going to compare both groups to that center. Well, that's exactly what an F-test does. That's what an ANOVA does. So zeros and ones are sort of t-test approach. Ones, negative ones is more of a ANOVA approach. So let's look at how this might, just quickly, how this might look. I have the rest of this sort of put together. So if I actually started to predict this all out, what I'd see is, one, if I use, this is using zeros and ones. So let's put that back again so you can see it. 0. Okay. So if you look at that, the average of that is going to be 0.5. The standard deviation of all these scores around 0.5 is 0.527. All right, so we get that. But look at now X bar. So if I take each of these, 0 minus 0.5, I get negative 0.5. So all these are going to be the same negative 0.5s all the way down, and the same 0.5s down there. So I can start the y minus y bar is all of these, 9 minus 5, right? We're getting all these deviations for y, and I'm just cross multiplying them. Right? So these are the products. 0.5 times 4 is negative 2, negative 0.5 times 2 is negative 1, right? So here are the products. I can now add those all in and get a sum of products of 10. With the sum of products of 10, so if my SP over, say, n minus 1, if that equals 10, it's negative, right? Negative 10. All I got to do is divide by n minus 1. Well, I have 10 subjects, right? So that means I'm going to have 9 degrees of freedom there. What's 10 divided by 9? 10 divided by 9 equals 1.111. This equals 1.111, which is my covariance. All right, what about correlation? Well, I can take that 1.111, I can divide that by the 2 standard deviations, so 0.527 times 2.404, right? 1.111 divided by 0.527 times 2.404 equals 0.877. With me so far? So far, this is not super interesting, but here's where it starts to get fun. The slope. Same 1.111 divided by the variance of x. That's now going to be 0.527 squared. So 1.111 times divided by 0.527. 1.111 divided by 0.527 squared equals roughly 4. 4.0003, roughly 4. Okay. Great. What about the intercept? Intercept now is going to be the mean of y, 5, minus the slope, 4, times the mean of x, 0.5. Basically, 5 minus 2 is 3. Did I get that right? 5 minus 2. Yeah. So I get a y predicted equals 4 times x plus 3. Right? Did I miss anything? Oh, no, sorry, I just realized what's going on. This is negative. This is negative. That's negative. Does that. Does this. This is negative 4. I was like, this is driving me crazy. Okay, so it was making me a little nuts. Trying to figure out why that was happening. But right, so everything should be negative. So this should actually then, sorry, this should be negative 4. So that makes this a positive. This is not this, not 3. Sorry, I forgot that, like, the oldest sort of dumb mistake in the book is not then carrying the sign, right? So because this is negative 4, this is actually 5 plus 2, which is 7. So this is 7, not 3. Sorry about that. All right, so y predicted, when x is 0, we expect y predicted to be 7. All right, so my y predicted for all these is going to be 7. Well, why? What's 9 plus 7 plus 6 plus 7 plus 6? I just summed up all the scores, all the depression scores for the control group. Divide that by 5, and I get 7. So 7 represents the sort of mean for the control group is 7. Right? So when x is 0, meaning we're in the control group, what do I expect from my control participants? Well, all I really know is their group, so I'm going to expect their group mean, which is 7. Okay. What about when x is 1? When x is 1, I expect the other group mean. 3 plus 1 plus 3 plus 4 plus 4 equals 15 divided by 5 equals 3. So the mean for the treatment group equals 3. So if I plug in 1 here, so that's negative 4 times 1, that's negative 4. Negative 4 plus 7 equals 3. So when I plug in 1s for the treatment group, it actually tells me that this -4 is how far apart those two groups are. So when I plug that in and add in the intercept value, it actually gives me the expected value for treatment, which is the mean of the treatment group. Just when you use these dummy codes, it actually turns out that it's going to whatever group, in this case, the control group gets 0. Well, we're going to make that 0 be the intercept value. And then the slope just tells us how far apart is the control and treatment group. Well, they're 4 units apart. As I go up from 0 to 1, I'm going down 4 units, which is why the slope is negative. So let's just set this up. So now if I'm testing this slope for significance, I'm basically saying, is a -4, that difference, significant? I'm basically doing a t-test. By setting it this way, I've created a t-test and set it up so I know what the control group mean is, and I know how far the treatment group is away from the control group. That's sort of why we use these sort of 0-1 codes. Questions about that? So what would you expect to happen if you did that? That's actually what I started to do by accident. Because if I did that, then the 0.5s and -0.5s would switch. So all of these negatives now would become positive. You with me? Which means I now have a positive 10. This becomes positive 10. That becomes positive 1.111. This is positive, so that becomes a positive correlation. Positive, so I now have a positive slope. The slope remains the same. But as I plug this in, 5 minus, because now it's going to be, minus 4 times 0.5, right? It's now gonna tell me, because I made these zeros, it's gonna put the intercept at the mean of the treatment group, which is 3. 5 minus 2 gives me 3. That's sort of what I started to do by accident, by not carrying the negative. I had flipped the 2 around. The interpretation would be the same. They're still 4 units apart. The treatment group's still 3 units below the control group. All that stuff is the same. It's just we switch the signs by switching the code.